great opportunity here to stand in front of you today and talk to you a little bit about innovation in rubber. And when you look at sort of the general perception inside the industry and outside the industry, there's why innovating in rubber? Rubber's around for 150 years or so, right? Well, I'm going to tell you there's a lot of stuff happening, and that the application and what's going on in the different industries require next generation of elastomeric materials, and that's where we all come in. So this is clearly an innovation talk. It has a little bit of technical content. So you know, what doesn't kill you makes you stronger. And so we'll get started here. So the beginning is really the case for change in some of the fundamental global trends that are going on, and the mega trends that are really driving this. And then I would like to show you 3 different stories. And these stories are where we take a world-leading capability, where you have to invest in a world-leading capability and use them to develop a new elastomeric material that makes a difference in our industry. So, the #1 underlying megatrend is population growth. That is a big driver to the growth everywhere. And it's kind of an interesting fact. So first of all people ever born, 7% are alive and well today. Think about that. Out of everyone ever born in the history of mankind, 7% of those are alive and well today. Well, maybe not well, but are definitely alive. And if you look at it, the growth rate, the population growth rate actually has declined. It peaked in the early 1960s at 2.2%. And it's about 1.1% now. And it's expected, the current models, to come to sort of a steady state around the year 2100, where deaths basically offset new births. But it's a massive change. Just in the 1950s, in 1950, the global population was 2.5 billion. That's 1/3 of what we have today. It's really mind-boggling. The planet has not gotten bigger in that same period, from what I can tell. Farmable land, as a matter of fact, actually over the last 100 years has declined by a couple %. So all of this has to work with the existing resources, if anything, slightly declining resources. And it leads to fundamental global trends around urbanization in megacities, right? People are gathering, it's the most efficient ways to congregate. You see more and more of those cities that have 20 million plus in the metropolitan areas, growing all over the world. It's a growing middle class. More and more people want to grab value out of this. They have more buying power. They expect certain things. Sustainability is a big trend that's happening. It's sort of the obvious green, but it's that fundamental drive that more and more people on the same planet and not more really resources. We have driven a lot with productivity around agricultural and so on, but there's only so much you can do. You cannot live in a way where it's just basically on a sustainability credit card, right? You're just going to keep charging without having any idea how to pay it off at some point. It just will not work. The population growth is too fundamental. And with it comes then this entire, one way to optimize is going smart. You will see more and more devices, artificial intelligence, and those kind of things. So just 2 years from now, when you think about it, we're going to expected to be 75 billion connected devices. So we're 7.6 billion today, and that means 10 devices per person, just 2 years from now. And there's a big population around the world that is not really participating as much. So, and then if you look at the CEO of SoftBank that has some sort of interesting predictions out there, 30 years from now, it's about 10 billion people that roughly matches this with a declining rate and so on. He expects 10 billion also smart robots that you have to kind of get together and work with. And 1 trillion connected devices. Anything from something as thermostat, anything that will interact with you and will hopefully look for the most optimized path in how we work. So what does this mean for the elastomer industry, right? Elastomers and rubbers are, in the end of the day, they're important critical materials, but they're enablers. And so things have to last longer. You can't afford a lot of waste. If you have a process that produces, let's say, 1 pound of waste on 2 pounds of product, that's not sustainable, not with those kind of population growth, those kind of growth drivers, right? There's a lot more drive. You talked about the middle class. There's a lot more around health, around safety. Those are very, very important kind of drivers in there. We talked about smart cities and so on. So how do we play in there? And I just want to give you an example. I'm not going to go through all this, but how do we play in these drivers? Now take the very first one right here, fluorosilicon rubber for turbocharged hoses. What the heck has that to do with more sustainable? Well, it enables something. So if you look at where the automotive industry is going, let's ignore EV, we get to that a little bit later, electrical vehicle for a second. Let's take out the traditional, gas-powered or fuel-powered engine. The car manufacturers cannot give on performance. In the end of the day, I'm German and I have the microphone, so we're going to use a German example. So if you have a big BMW, you cannot go down in performance. One way to become more fuel efficient is just put an anemic engine in there and just, zipper along. No, you still expect the next generation of the 5 Series to be better than the previous. That's just that's the basic. Otherwise, you kill your badge and your reputation. So how do you get more out of an engine? So you downsize the engine. Turbo technology is that. Turbo technology requires now materials, hoses that are exposed to they have to be flexible, they have to last for 10 to 15 years, they have to get exposed to very high temperatures, have to have fuel resistance. Now you get all this, right? So now you can get out of a 2-liter engine what used to require a 4-liter V8 or something in a turbo. Now that downsizing that engine, now you can get collateral benefits because you can down-gauge other parts of the car, and so you get weight savings and fuel savings by just a more efficient engine. So let me go to the 3 examples that I would like to share with you today. And the first one involves what we call high throughput technology. When you go through the classic way to do science, and it's been like this since the Stone Age pretty much, you think of something, you run that experiment, you analyze and characterize what happened here, you draw some conclusion, you go back with this new knowledge from your experiment, you go back and maybe do the next experiment. That's been how we have done science all the time. What we have done in Dow is change this to a massively parallel system. So instead of a single experiment, we start now with an array with, let's say, a plate of 8 times 12, so that's like 96 different experiments. So it's a design of experiment, right? So you lay out all the different parameters you touch. You can actually put some replicates in there. Replicates are not cheap, right? So you get a sense of how solid, how robust your system is. Then you run your experiment in this 96% reactor at different temperatures, pressures, so on. Then you analyze it. So you have to massively parallel that characterization part too, because what you can't do is run hundreds and thousands of experiments and then there's one poor guy in the analytical lab who's totally overwhelmed because all these data is coming. So you have to do that, the robotic systems around that one. Then all this data is now going to get harder and harder to just look at in line item by line item. So you have to develop visualization software to see what are the interesting spaces now to go from your design of experiments and you're going to do that cycle again. One example that I would like to, we have used that in formulation, in even in application things like coding, synthesis, characterization, in any kind of area. But the area I would like to highlight today is the area of polyolefin and olefin polymerization to make elastomers, right? So in the 1950s, when Ziegler and Nabat discovered how to make polyethylene, that was the start of all this. It was a heterogeneous system. So you basically take zirconium chloride or something like that. You activate it with an alkyl source, and it does stuff. And by empirically changing stuff around, you can actually get some pretty good sense of some of the different polymers that you can make. And then the breakthrough came in the 1990s when you started to, I don't know if this has a, yeah, here. When you have these single metal catalyst systems, either like metallocene here that is bridged, or a CPM system, and with these now you could have this organic gunk around that metal, and you can change that, and whatever you do here will have an impact on the molecular structure of the polymer. By changing the molecular structure of that polymer, you get now an elastomer that has unique properties. So this catalyst to polymer to final properties is the key connection. Then the research started. We used these high throughput tools and run literally thousands and thousands of catalysts to get the molecular weight up, to get higher efficiency and so on, better branching or better control over the branching and so on. And ultimately discovered, actually, and that's sort of one of the great stories here, is this chain shuttling chemistry. And what it does is you have two catalysts now working together. One catalyst, the one with the zirconium, only likes ethylene. Ethylene doesn't lead to a polymer. The other one actually doesn't care. It takes ethylene, it takes octene, it takes any alpha olefin that you're going to give it to it. And the way to make blocks now is that as the polymer chain grows, let's say the polymer chain starts at this metal center and it incorporates anything, then it toggles by a chain shutting agent to another catalyst that only does ethylene, so you get these blocks. And now that gives you some unique structures. These blocks of more elastomeric pieces to very crystalline pieces gives you now unique properties that are really, really exciting and have lead to really exciting thermal versus elastic properties. And so on. So you can really define the properties of your final elastomers in there. So when you look at that, you can make those elastomers more thermally efficient. You can tailor the polymer structure. You can play around with the monomer composition. You can play around with the polymer dispersity and so on. So you can really get a very predictive and functional approach to, I want those kind of properties and I'm going to drive this by doing this with my catalyst system. That kind of correlation is really what is new around here. But this process not only gives you more control of the final property of the molecule of the elastomer, it also is much more sustainable. You can run this at high temperature, and it makes it actually much more efficient in terms of molecular weight gain. The classic Granada approach leads to a lot of side products, salts, metals, and so on that you can now wash out, and that you don't have to wash out anymore. It's a much cleaner reaction, and so on. So you now have a bunch of benefits by running. This is normalized by pound basically. You have much lower energy, much less impact on ozone, smog, and CO2 resistance. So it's really it has the sustainability impact as well as the impact on the polymer properties. But the key in all of this is to use the latest and greatest of high throughput technology, robotic technology. We now have more than 400 fully robotic systems to run reactions, analyze the properties of these types of materials that we make, and so on. That gives us the control to adapt to new applications as they come around. The next area I would like to cover a little bit is the area of analytical science. And actually, within Dow, that is the oldest lab. That's the oldest capability that we have. The analytical lab was actually founded more than 100 years ago. It's now many hundred people that work in different types of settings. We don't use the analytical lab as a service lab, as a control lab. We use that as how to find out new methods to understand exactly what happened. A lot of it is around elemental composition. If you have any kind of method that you can see to find out what elements are in there, as a matter of fact, we don't play this up too hard, but we still operate a small research nuclear reactor because it's the most, using neutron diffraction is the most efficient way to get to the chemical composition. Structural, obviously NMR and so on. We also have a microscope. We have one of the 3 most sensitive microscopes. So if you look at a carbon-carbon bond, it's about 1.5 angstroms. Our best resolution is 0.68 angstroms. That's 0.068 nanometers. That's the resolution of our microscope. So you can actually look at things and you can see all the different patterns and how they're arranged. That sometimes is absolutely critical. And we can go on and like this. Obviously, we have a lot of experimental equipment also around polymer properties and so on. So all these kind of things are absolutely essential because only if you really understand what's going on is when you can draw back and really, take the next step in terms of figuring out what actually happened. And the one area that I would like to show, or that I would like to highlight is an area that we're really excited about, is around optical moldable silicones. Silicones can be formulated in an elastomer that's extremely clear. And because it's an elastomer, and because you can injection mold it, you can actually get to geometries that are impossible to get to by glass. You would have to machine or polycarbonates or other ones. Now, in order for silicones to be strong and tough enough, you have to fortify them. And the way you do this, you put typically silica, or you put fillers in there. And most often some sort of silica, cubic silica, or whatever, what have you. The problem is those are microscience particles, and they lead to a non-clear system, right? So what we discovered here is that if you can take our internal, if you take resins that act kind of like nanofillers, you put them in there, they give you a structural reinforcement, but they do it below the wavelength of light, and now you get entirely perfectly clear systems. We use this, the application spaces are everywhere. You can do it for street lighting, stadium lighting, unique LED encapsulants, and also automotive lighting. We'll talk about that in a little bit. But that's the key. So the problem that we have initially, though, is just turned a little bit yellow. And what you have to have for this technology, it has to be absolutely clear over the lifetime of the material. In this case, it actually turned yellow already early on, so we had no idea what happened, and we tried to figure out. So this is when we got really engaged with the analytical labs, and they went in there. They're kind of the CSI of chemistry for us. They go in there, they look at everything, they dive into it, and they found that there were a couple of impurities in there, parts per billion in the lower levels, but they were in there. Where did they come from? We had no idea. We checked everything internally, every manufacturing process, what have you. It was until we figured it went upstream in the supplier base. And ultimately, we found that a rubber hose at one of our suppliers in one of their processes added a teeny tiny impurity that carried through and made these materials just a tint yellow and unacceptable for our applications. But that's where you have no prayer if you don't have world-class analytical capabilities in-house. So I mentioned we use those types of, these types of applications are used for all kinds of different lighting application. We see them now even in Internet of Things applications and so on. But I would like to show you one application that I'm really personally excited about, and that's on the automotive headlamp assembly. So traditional automotive have high beams and have low beams, and the trends in automotive are that can you make anything in the car, honestly, lighter? Can you make it more adaptive? Are there ways to make sure that you don't blind people, that you can block out anything? And of course, lighting, the headlights, I think Audi was really the first pioneer in this. Headlights are not really just, you know, for looking at that. It also has a statement. It can define your brand, how this looks like. I think when you see a headlight of an Audi right now, you know it's an Audi just because of how they position themselves. With that, we work together with the value chain. Our tier one called Hella in Germany, as well as Mercedes was the OEM, and devised an entirely revolutionary new headlamp technology. So I'd like to show your attention here. So you still in the front, you see you have some secondary optics that just remind you of any other, you know, front of the vehicle. But behind it is actually an array of 84 independently controllable LED chips. And they're connected via 84 different light pipes into a lens assembly that's kind of curved here. So you can see the front of this. This is what you see from the front of the car, right behind the secondary optics. And then on the back of this lens here is the light input side with these 84 different light pipes. Now think about this. This assembly, this one part, has to last for 10, 12, 15 years, ideally. It has to be perfectly weatherable. It can't yellow, it can't get brittle, it can't get anything. It is very, very fragile. I wish I had one with me right now. These little light pipes are very thin, very small. They have perfectly the same length. You know, I drive a lot in Michigan, and there's some potholes here and there, and none of them can break. It has to be elastic, and so on. It has to be perfectly clear. So when you think of what you're asking of this particular part, it is just remarkable. And so how does this entire technology work? And I have a video now, but I would like to give you a little bit of a sense. So the way this fully integrated system works, and that's why the OEM, the tier one, and the material supplier have to work together, is that you have a bunch of sensors in the front of the car. These sensors constantly look what's going on in front of you. They feed back to those LEDs, and they'll block out certain parts, as you can see. So I'm just explaining this because I think it even comes with some kind of soothing music. So and then it fires, it deactivates or activates certain LEDs, LED chips as you go along. So let's roll the tape. So you see the car now coming from the right side into the picture, and it goes along. And now it starts sensing there's a car coming towards it. And now it gets close. Now it starts deactivating certain LEDs out of this. And at less than hundredths of a second, it feeds back all the time. So all these angles are now blocked out. And as the car moves towards it, it constantly changes and adjusts it. What does this mean? In the end of the day, you're driving around with high beams at all times without blinding anyone. That's a true safety feature. Come back to these global megatrends. That's a true safety feature. Always high beams. And here's another example where sometimes legislation is behind innovation. Unfortunately, Mercedes has to deactivate the system in the US because there's a Nixon-era regulation that every car has to have high beams and low beams. And so this one, we don't know, so it's not allowed. So it's active, and it was just recently introduced, and it's running in Europe, and it's moving to Asia, and we're working with our friends in Washington to maybe get some sense. We think that's a little safer. The last one is an area that is, I think, coming more and more. It's modeling, artificial intelligence, augmented reality, virtual reality, all the stuff that's happening right now, and how we play in that one, I think is going to be very important. And one area that goes with that is 3D printing, customization, additive manufacturing. I think it's a huge growth area, and where do elastomers play in this one? I would like to, in my last story, talk a little about that. When you look at the area of 3D printing, it started, 30 plus years ago. It was driven by equipment manufacturers looking for just a material that's easy to handle. So I have a nozzle, I can heat some stuff up, so give me some sort of thermoplastics and I just run it through it. I'm gonna make it liquid and then I add it in there and then that's how we're gonna do it. So ABS and materials like this were used. The key now is really, okay, how about other technologies? We want to, you know, in the end of the day, we would like to 3D print anything and everything. Well, that's where the equipment manufacturers are actually over the head. So now you have to, now that's where the materials guys come in. And in this particular example, I wanted to show you a little bit of how we took this 3D printing concept and brought it to silicone elastomers. Silicone elastomers are thermosets. You have to cure them. So this is not that easy for equipment manufacturers anymore. And as I said before, a lot of those big challenges, not one guy can do it alone anymore. Just in that automotive example, there's no way Mercedes can do it alone, there's no way Hella can do it alone, there's no way we can do it alone. We have to work together. In this case, it's actually a collaboration of three different parties. It's R.D. Abbott, that is quote-unquote a distributor, but they're not. They're actually an innovation and technology partner for us. So the two of them, more from the material side and the application side, and then German rep from the equipment side. And what you can see here is that you'll see a video that's time-lapsed, so it's very busy. It's almost the opposite of the previous movie where you had that soothing music. This looks very hectic, but it's time-lapsed. It gives you a sense, and the idea is that a very thin bead gets applied and basically takes this entire layer and lays down wherever that layer of that part has to be. And then you will see this a very quick infrared flash cures this, and then the printing head comes back home and draws the next layer. And what's really phenomenal about these 3D printing applications, it used to be that there was a big difference in the mechanical properties of a printed part and, let's say, an injection molded part. Those times are over. Now, you can actually print and the final properties are statistically indistinguishable from something that's molded. So I think that's really where a lot of the exciting new technologies have happened. You will see, I'm going to start the video. So this is the most boring part of anything. It's an ASTM slab, so there's nothing exciting about it. Anything ASTM, but you have to, it's a good way to see how this, and you can make almost any intricate part that you would like. So you can see how the print head is now moving along, going back and forth in real time, obviously a little slower, and just it builds this entire slab. Next layer comes, just goes back. And you see that IR flash cures this quickly, and it builds on it. Think about the technology. And then you just take it off, and you have a perfectly clear printed part. But think about the technology. So it has to cure fast. It has to have enough adhesion instantaneously. And it has to interlock with the previous layer that just has been cured, right? So when you think about the molecular design, it's not that easy anymore. Now on the equipment side, those guys have to bring this like cure cycle in there. They have to make sure that if you have this infrared, that it really covers every part of every side and every portion of that part equally, because you need to have full cure. And so it just gives you a sense of what you can do. But what does that mean for us? In the past, what happened is, let's say you're looking at a new, I don't know, kitchen tool, or that's probably not so exciting, but an automotive or consumer good, like a cell phone with part or something. You start with a concept. You do some ideas of what you would like to do. You design the part, maybe on a computer in a CAD design or something. And then you have to kind of make a mold, test the mold. Then you have to mold a piece. Then you look at that first conceptual prototype thing that you just molded. Making a mold takes forever, and so on, all these steps. And then you test that, and then it turns out that's not good enough. So we're going to go back to the drawing board, and so on. With this now, you can just accelerate through all of this. You think about get a new part design concept into a part design. You just print that prototype right there, and you start testing it in your feedback. These printers take a CAD design and directly print it whatever you want. And I think that's really where the value comes in. If you need any further justification, you can just look a little bit at our rough price table on the left and versus the right. It's just a few $100 to basically make a prototype after another. But the key is the time. Within 3-4 hours, you have a new part that you can now fully run through the battery of tests. You can go right back to the drawing board and run through it and make the next one. So I think that this is really where things are going, and we're not going to stop here. What if you want to have materials that are, or a part that consists of multiple different materials printed together? There's challenges everywhere, but that's the exciting part. The more you can do here, the better. And for us in this industry to stay really relevant, I think you got to be always one step ahead. So if I look at 3D printing, we have made a lot of progress. When I'm really honest, we're just at the beginning. We're just at the beginning. Where this is going to go over the next 10, 20 years, I think is absolutely phenomenally exciting. Those are the players that work together, and again, what you also will see more and more in this industry is there's not one DAO that's just going to push some technology out there and like you guys figure out what you want to do with it. That's not how it's going to work anymore. It's us all working together closely along the value chain, finding new applications where neither one of those in the value chain had a chance to do it themselves. There's a couple of really interesting applications. Obviously, these are elastomeric silicone, these are silicone elastomers that are printed like this. Very, very intricate shapes. No mold whatsoever. As a matter of fact, try to kind of get a mold ready for this. That's not easy. There are many part design now that are only accessible easily via 3D printing, and I think that's exciting. One application that we're using is, and that's I think where this entire customization comes together, is we're working with a Danish footwear company called Echo that where you can go into a store. And they'll look at how, your biomechanics, how you walk, how your footprint, they're analyzing you from different angle, and then you just go to Starbucks across the street, have a coffee, and so come back, and now you have a sole that's exactly and only printed for you. And not just looking at your, not just looking at the bottom of your foot. It's how you walk, how you hit everything. It gets encountered. That is kind of the future. This ultimate customization, and where we are sitting right in the middle. Our elastomers and rubber technologies are right in the middle of all of this. So I think hopefully, I'm on a roll right now. I'm very excited about where this industry can go. Just a couple of words about how the new DAO is going, because we're in an interesting arrangement of where we came together with DuPont and are now falling apart into sort of, it's a forced marriage with a scheduled divorce. And we're one of those that are getting divorcees, I guess. And I think we're a more focused company now going forward. We have all these building blocks in there, from silicones to the olefins and so on, and we're driving that into using these different capabilities into our key markets. But when you really look at the elastomer industry and where we're going, I think that the applications will be more and more demanding. It'll be more and more growth, but they also will be more and more demanding. In terms of weatherability and where we put these elastomers, right? If you take a classic gas-powered vehicle versus an electrical vehicle, the heat map is changing entirely. It all was at the engine in a classic vehicle, right? That's where the heat, and then wherever you're further away, it's less and less, heat is less and less of a problem. Electric vehicle is entirely different from from the DC converter to the battery pack to there's other parts of the vehicle that are much cooler now, and there's other parts that are much hotter. Thermal management of all the electronics that are in the car. It's going to be very exciting and how we're going to play in there. And I think we in the rubber industry, we cannot afford to stay on the sidelines. We got to be in the middle of all of this, help, working with the value chain, showing where the applications are, where are new elastomers needed, and drive innovation into exactly those things. I'm not going to go through all the possible to all the applications and that we can see, but it covers pretty much every industry, from mobility, transportation, anywhere, into the consumer space, industrial, electrical, wherever you look, you will need some elastomeric materials. And I think if we stay ahead, if we engage in an innovative way with the value chain, we're going to live long and prosper. Thank you very much.